Chris started his career in laptop work at the Tevatron, and after his PhD in 2001 from Columbia University, Chris joined the CDF experiments, working first on doubly charged Higgs boson and later on doubly mass measurements. In 2006, he joined Atlas with direct contributions to several analyses such as W mass, Higgs discovery of its decay to W boson pairs, and W boson production through vector boson fusion. So during this time, Chris convened the tracking group, the very exotics and exotic physics group, and the electroweak physics group at CDF, and served as Atlas contacts at the LHC Higgs working group for the gluon fusion and Higgs properties working group. Currently, he's measuring dye-tau production at Atlas and tests to be anomalies and serving as an ECFA working group convener. Today, he will talk to us about the high precision measurements of the W boson with the CDF II detector. So Chris, please go ahead.
Let me unmute. Okay, thank you for the introduction. And so today I will describe the measurement of the CDF measurement of the W boson mass. And to begin with, I'd like to first motivate why the W mass is interesting and why it's interesting to measure. So it's interesting to begin with just because the W boson has mass at all. So the existence of its mass is evidence. It was evidence. It suggested this Higgs, the Higgs boson. So you have this Higgs field potential, this wine glass shape, and oscillations along the radial axis give you the Higgs boson. But then there's a degeneracy in the along the phi in the complex phase direction. And so this in the phi potential, but this the breaking of this degeneracy, so the choice of a vacuum by the Higgs field in nature, gives you a position that then affects the potential of the gauge bosons. So you can write down the gauge field potential that arises from this, and you get mass terms for the W and the Z bosons that depend on the value of the vacuum expectation value, and then the weak and the UN couplings. And so you can then write down what the W mass would be from these couplings. And given the measurements of the Z boson and the electromagnetic coupling and the weak coupling, you then infer from this tree level Lagrangian picture a W mass of a bit below 79 GeV. So that can't be the whole story because we know the mass is considerably higher, and that's because of quantum corrections. And so in the case of the W and Z bosons, the leading corrections are from the top and the top bottom loop, and due to the difference in the top bottom masses, that you get a significantly different correction for the W than you get for the Z, a few percent difference. So if you write down the mass of the W in terms of the electromagnetic coupling and the weak constant and the Z mass, you have a set of radiative corrections, and this largest correction from the top bottom loop gives you is proportional to the top mass squared. And so then you put in all of the quantum corrections in the standard model, you get a indirect determination of the W boson mass of 81,354 MeV with an uncertainty that's roughly equally due to the missing higher order corrections in the loop diagrams, which is about 4 MeV, and then from the other input parameters such as the Z mass and the top mass. These are highly related to the Higgs quantum corrections. So you can see the Higgs corrections has the same top quark loop, but in the case of the Higgs corrections, you don't have the gauge symmetry to protect the mass of the boson. And so if you integrate, just naively integrating the effect of this loop up to some very, very high scale, you get the correction to the Higgs mass grows as the square of this scale, and so And so if there's no new physics, you would need some sort of tuning, some cancellation between the loop corrections and the input parameters in the Lagrangian. And so if you wanted to cancel these corrections, you would need, if you wanted to say 1% fine tuning, you would need a new physics at a scale of around 6.5 TeV. So this is motivating. This is a motivation of new TED scale new physics, and you can see that this naturalness, this hierarchy or fine tuning issue is related between the Higgs mass and the gauge boson masses, and so the W mass is very sensitive, observable to any source of naturalness. So explanation for this naturalness issue. So a classic example is supersymmetry, where if you have supersymmetric partners to the tops, you can have opposite sign corrections in your loops to cancel the effects and leave a small residual mass for the Higgs. And then you would get supersymmetric corrections also to the gauge boson masses, which would be different for the W's and Z's. You get different because of the different masses between the stop and the spot and so on. And so you'd have different mass shifts for the W and Z, and you would predict it would affect the W mass that you measure based on the standard model prediction. More generally, you can write down any different, okay, so in the case of this, I guess in the case of supersymmetry, you can write down the difference in the corrections to the W and Z propagators using this rho parameter. So that delta rho is effects of new physics on this rho parameter. And so you can write these down in supersymmetry, for example, for these stops and spot-em loops with this function. And then you can translate back to the W mass to see what the impact would be for various squark masses. And so for relatively large gluino masses and sort of smaller spot-em and slepton masses, sort of roughly consistent with limits from the LHC, you can see what the stop quark mass range would be. And so as you go to higher W mass, you need a smaller stop quark mass. And in this scan, the ranges were, say, for 80, 430 for the W mass was something like a few hundred GeV for the stop quark mass, up to a little more than a TeV. And so yeah, more generally, you can write down any new physics effect on the propagator, the W mass, in an effective field theory. So where you expand, you add terms to Lagrangian that have higher dimensions with suppression over some new physics scale. And so the leading terms are suppression over the leading physics scale, the new physics scale to squared. So you have some blob from the new physics effect in your propagator, and you can write down the fractional effect on the W mass in terms of four parameters for Wilson coefficients for different operators. So the first one, the CHD, is something that affects differences between the W and Z masses, and something like a Z prime could do this. And so if you just put in order 1 coupling, effective coupling, you would get an effective scale of order 5 TeV, a little below 5 TeV. In the case of the CHWB, this has to do with the mixing between the weak and U1 gauge symmetries. And so here, if you put in an order 1 coupling, you'd get a scale of order 6.5 TeV. And the last two terms are due to the weak, the 4 fermion coupling, and the weak mixing, the weak measurement, the weak coupling from determined from muon decay. And so that if that muon decay has new physics in it, that diagram, then you would have a difference in your prediction for the W mass. So in all of this, if you lower the effective coupling, so these order 1 couplings are sort of roughly as high as you might go, maybe a little higher. You get a bit higher scale, but then if you lower the couplings, you'd have lower scales. So generally, if you have something like a 0.1% deviation in MW, you would expect something of order 10 TeV or less in new physics if it's due to some high scale physics. Okay, so that's the motivation. So now I want to turn to the measurements. And this is a summary of previous measurements, and including this one. So on the left, we have the individual run 1 Tevatron measurements from D0 and CDF, and then we have the individual LEP measurements. And then we have run 2 D0 and the recent and Atlas measurement, and then the new CDF measurement. On the right, we have the LEP measurements combined, and then also this year LHCb came out with a measurement, so the measurement from LHCb is also shown on this right plot. And you can see the difference between those measurements and the new CDF measurement. So I want to describe the CDF measurement. If you're not familiar with the Tevatron, it was a 2 TeV proton-antiproton collider at Fermilab in Batavia, Illinois. And so the Tevatron collider is shown in this picture. The main injector fed in the antiprotons. CDF was located along the ring near the high rise at Fermilab. And CDF detector had is a standard detector that had an inner silicon vertex chamber, which you can't see in this picture, but is behind this inserting rod there. But then on the outside, there was a large open cell drift chamber. And then outside of that is the calorimeters, coarse calorimetry. There's 24 segments in phi as you go around. And then there's the Muon detector, which is outside all of this structure. The data set that is used for this measurement is taken between 2003 and 2011. There was a run 1 data set in the mid 1990s, and then this in the early part of the 2000s there was some commissioning, and then the luminosity rose over time, and the first 4 years of data taken corresponded to a previous measurement, and then adding the most recent 4 years, because of the higher luminosity, that it quadrupled the overall data set to use for this measurement. So the bottom picture here shows the mean number of inelastic collisions, and so you had in the previous measurement you had a peak around 1, and now you have a peak around a little below 3. So it's nearly a factor of 3 more collisions, but in the overall number of collisions, it's still relatively small compared to, say, Atlas and CMS. Okay, so that's the data. So now I'm going to go into a little bit about how we do the measurement, and then what we need to do for the measurement, and then some of the details. So the process, the final state is the simplest final state we can measure. It's a single charge lepton. So we measure the W boson decays to either electron or a muon and a neutrino, and we fit the mass. So we don't have we don't know the neutrino momentum along the z direction. So we have a transverse mass distribution, and so we have to have templates to fit for the invariant mass of the W boson. And so this plot on the left shows what it looks like if you vary the mass by 100 MeV, and you can see very small shifts in the small differences between the blue and red lines. If you take the ratio, it's a bit easier to see. You can see that there's a very sharp rise around the W boson mass. So that's what gives you the statistical power from this distribution. And you can see that for 100 MeV, that's a couple percent, a little more than 2% rise around 80 GeV. So in order to get this level of precision on so actually we are able to get statistically a factor of 10 better than this. So a few tenths of a percent variation between low MT and high MT. So in order to get that precision in our calibrations, we need to have sort of a few tenths of percent level precisions, in some cases better than that. So for the case of the charge lepton momentum calibration, you have to have a very precise knowledge of its momentum scale and the resolution of your detector in measuring this, the charged lepton momentum. So on the bottom left shows that what happens if you vary the charged lepton momentum by 0.1% on the charged lepton PT, so it's barely visible there. In the ratio plot, you see a couple percent variation. So so we're wanting to get something that's an order of magnitude better than this, so something of order 0.01% in the precision of the charged lepton momentum scale. For the rest of the event, we have to measure we have to infer the neutrino momentum by measuring all of the other energy in the event. And so we sum up that energy. So it's the together it's added as a vectorial sum to give us the recoil momentum, which is balancing the W boson momentum. And so this we don't need to know as precisely, because we require it's sort of averaging out, and so we need to know it to sort of, so 5% variation gives you a couple percent change in the shape of the neutrino momentum spectrum. So we need to know it to about 0.5% precision to get sort of a 0.1, 0.2% changes in this spectrum. Okay, so to do these calibrations, we developed a custom detector simulation for this analysis. So we had to model all of the charged lepton physics, so all of the ionization energy loss, multiple scattering, the Brownstalling, the photon conversion, the Compton scattering inside the detector to understand to calibrate the momentum scale and the resolutions to required precision. And then we had to have various models of the detector components. So working from the outside, that the Muon detectors, we have an acceptance map that we get from the full simulation and check with the data. Within the electromagnetic calorimeter, which is where we measure all the electron showers, we had a detailed J-4 model of these showers. And then the outer tracker, which measures all the charged tracks from both the electrons and the muons. There we have hit level, layer by level hit resolution functions and efficiencies. So there's 96 layers in this chamber. So we have broken up into 8 groups of 12. And so each group of 12, we have resolution functions and efficiencies. And then on the inner bit, there's a silicon detector. We don't use the measurements from the silicon detector, rather because what it can give you is vertex position, but we know this is promptly produced charged lepton. So we actually constrain the charged lepton track to the beam position. And so this gives us a better, as good resolution and a little bit better even than using the silicon measurements. And also there's a challenge in aligning the silicon relative to COT that we then don't have to worry about by doing this. So we have to, the main thing with the silicon is to worry about then is how much energy loss and how much scattering is going on as the charged particles go through. And so we have 32 slices of this, and we have the radiation lengths and the modeled in a map. And so this is a phi-z map example, and in the middle of that, where all the cables are. So there's overall about 20% radiation lengths in the silicon. And this map is showing sort of the bulk of it, which is the cable is about 5 to 10% radiation lengths in this region. So that's our simulation, that's our tool. So then we can go and start with that tool, we can start calibrating the charged leptons. So we start with the tracks, using calibrating the tracker. And so the first step before we go and make the momentum scale calibration itself is to align the chamber, so make the data as uniform as possible for the measurement. And so we do this in a couple steps. We have a step where we fix the the positions of the wires at the end plates, the two end plates that are holding the wires from end to end between the in Z. And so we do this by measuring cosmic rays in the data that we collect, but from the same triggers in situ with the measurement. And so this is an example track going through cosmic ray track going through the detector, and where we measure the outgoing track, and by default the reconstruction doesn't reconstruct the incoming track, but we have a special algorithm to reconstruct the entire thing and to reconstruct the two legs. And so by reconstructing the entire cosmic ray, we can look at hit residuals between the track and the wire and the hit positions, and then use that to adjust the angles and the positions of these of each of these cells. So each of these cells in the tracker in the tracking chamber has 12 wires, and there are 2,500 of these cells. So we have 2,500 symmetric shifts in our phi, and then we have another 2,500 for asymmetric between the east and west end plates. So we have 5,000 corrections, alignment corrections. And you can see an example for one symmetric for the inner super layer, sort of the one with the fewest cells. You're getting alignment corrections of 50, sort of order 50 GV in general, and sometimes up to 100 or a bit more. Microns, 100 microns correction. The other thing we have to worry about for the alignment is the shape of the wire between the two end plates. And so there's a gravitational sag of a couple hundred microns, and there's an additional piece that's put at the center of these wires to keep them separated. It's a spacer so that they don't have an electrostatic deflection to short. And so so you have a bit of this parabolic shape with this little dip in the middle. And so we use the cosmic rays to look at the two legs of the track, the incoming and the outgoing leg, and look at parameter differences between the incoming and outgoing leg as a function of phi and as a function of Z. And so we can then check the wire shapes between the end plates, and we can make corrections. So there's the example correction on the right. It just shows various corrections as a function of the angle where you are in phi, and then whether the super layer is an axial super layer or stereo. So whether it's just going straight in Z, or whether it has a tilt angle between the two end plates. And so this is going out radially. So this does impact the curvature of the track that we infer. And so you can see on the bottom, there's some plots showing the difference between the two tracks, the curvature of the two tracks. Before you make the corrections, the black dots. So there's some curvature bias, and there's also a bit of shape, some dependence on cotangent theta. And so after we make the adjust the wire shapes, this is all removed. And you can see the initial curvature bias before we do any of the alignment. You have this shift, and then after it, we have this, it's centered around 0, and you can see it's considerably narrow. So we've significantly improved the resolution as well. So that's getting uniformity of the data. So once we've aligned the detector, we can go through several steps to calibrate the momentum scale. So the first step uses J-psi decays to muons. And so here we have the most, we have the largest data set. So we have the most, we can do the most studies with it. We can check effects in various as function of various variables. The first step though is to make sure that the shapes and the resolutions are modeled well with our hit level simulation. So we have to generate some J-psi events and adjust the kinematics so that they match the data, so that the resolutions match what we see in the data. And we also have to model that. So this is the resonance shape in a particular inverse PT bin. And this shape we have to, in order to model it at this level, we have to tune all the wire, the hit efficiencies and so on. We also have to include a NLO form factor for the QED radiation. Before doing that, if we just use the a leading log form factor, we don't get very good agreement in good chi-squareds, and so that improved the chi-squareds and reduced our systematic. It used to be one of our leading systematics, is understanding the effect of the QED scale on this line shape. So with the modeling of the J-psi line shape, so we also then have some corrections as a function of, as I mentioned, some various variables. So some things that can't be constrained by the cosmic rays. So one thing that can't be constrained is the length scale of the tracker, and this can affect the measurement of masses because you want to know the opening angle between two tracks. And so so we can plot as a function of delta cotangent theta the mass of the J-psi. So that's expressed in the form of the momentum scale correction of delta P over P. And so if you stretch or shrink the tracker, that will make your opening angle get larger or smaller between your tracks. And so we apply a small stretching of a few tenths of a percent, and that removes it before the correction is a small sort of parabolic shape, and that gets removed with that correction. The other correction we have to make is the amount of material in the silicon in particular. So there's a couple percent correction there, and that's determined by looking at the effect of energy loss in the silicon, because that goes logarithmically. Whereas if you look at if you mismodel that, then that will affect the low momentum tracks more than the higher momentum tracks. So you get a linear slope in this distribution of delta P over P versus the inverse PT of the tracks. So low PT, it's over here. You get some slope, and so with the correction applied, we get a flat line that can extrapolate to high momentum for the J-psi scale. So that's the J-psi calibration. So the next calibration we do is the upsilon decays to muons. So here there's not as many upsilons. It's a smaller sample, but it can be split up in several ways to check at a different range of momentum, and also to more importantly, it's to check the constraint that I mentioned of the track to the collision point, which is something we can't check with J-psis because many of them are produced from B decays. So here I show that the calibration with the beam constraint on the left and then without it on the right. And you can see first that the one on the left, you have a narrower distribution. So you see the benefit of constraining the track to the beam line. You get a 30% reduction in statistical uncertainty on the momentum scale calibration. And then you also can see the consistency of the constraint, the two measurements with and without the constraint. And this is something that was not we did not have a consistency in the previous measurement, and that was understood throughout the course of this measurement. And so now there's no, and there was a systematic applied to because of that, and now there's no systematic because due to the beam constraining anymore. Okay, having done all of these calibrations, we can then do our final calibration, which is first step is to actually make it as a measurement, the mass of the Z boson. So we had the Z boson mass blinded until all of these calibrations were complete. And then we unblinded and obtained a mass that's very consistent with the lab value and a factor of a few, within a factor of a few in uncertainty, overall uncertainty. Yeah, the blinding was a flat distribution of between -50 and +50 MeV, and so that was removed after these things were complete. The distribution on the bottom left shows what the best fit looks like for the Z mass, and then on the right we now show all of the scale, all the calibration points versus mean inverse PT. From the J-psis, the epsilons, which we do also split up, but we only show as one point here, and then the Z's, and then the combined calibration is shown as this cross in this plot. So that completes the tracker momentum, the Muon momentum calibration, and so then the next calibration we need to do is the electron momentum. And so here since we have this precise track calibration, we want to simply transfer that to the calorimeter using W and Z decays. And this is the way to get the most statistical power in transferring in obtaining a electron scale calibration, because the W's have the most of our electrons come from W's, so we can use the full W sample to do this. So the first step, again, is we want to get the data as uniform as possible. So we use this ratio of the calorimeter energy to the track momentum to remove time dependence and response variations in towers. So in the towers, there's this is a wedge of the calorimeter tower, and this is along Z, so along eta, and along eta, in between each tower, there's light guides, and so you have reduction in response near those light guides, and we have to remove electrons that go in those regions. But even sort of as you go away from the center, there's a bit of drop in response, so we correct for that. We also do a final calibration to make sure that tower to tower, the energy response is the same to within about 0.02%. So that's shown on the right is after we fit the E over P in each individual tower, what the scale looks like. And so that's, like I said, it's consistent. They all consistent with each other to 0.02%. So having done the uniformity of the data corrections, we then model. We then need to model the in our simulation the shower. So there's two aspects. We have to model how much energy is in the shower, and there's two aspects to that. One is to measure is to understand how much energy is being lost beyond the calorimeter, beyond the electromagnetic calorimeter. How much radiation there is being lost to the track before the calorimeter. So here I show a bit of the studies we did to understand how much is lost beyond the calorimeter. So the radiation lengths of the calorimeter is about 18 radiation lengths going through from the collision point to the end of the electromagnetic calorimeter. So with that number of radiation lengths, you get a few percent leakage out the back of that calorimeter of energy, and that's significant on the scale of what we're trying to measure here, which is 0.01% type precision. And so we need to model this shape of this leakage, which we get from Geant, and we parameterize it as a function of energy, and also as a function of the number of layers in the calorimeter, because this changes as you go forward in eta. And so we put this in our model, and we also then have a final small correction for a residual dependence of the scale on energy. So after the small correction is put in, we get a flat dependence of the electron scale on the energy of the electron, and that's shown on the right. So that's the piece of understanding the shower leakage out the back, and there are small corrections to the amount of radiation lengths, about 0.1, so a percent or two, a correction to the amount of material in the calorimeter based on the E over P distribution at low E over P, where there's where you have too little electromagnetic energy that you measure relative to the track. We also use the high end of the spectrum, so large E over P, where you have you're not measuring enough energy in the track because it's radiating photons, and so the track momentum is reduced, whereas the photons are collected in the calorimeter. So you get this, depending on how much material you have in your tracker upstream of the tracker of the silicon upstream of the COT, you get it changes the number of events that you get at these high E over P values. And so we use this coarsely grained E over P distribution to adjust again by a few percent the amount of material upstream in the silicon upstream of the COT. The other thing we have to model is the resolution, the peak, the shape of this peak. And so this we split up in these individual tower pseudorapidity, so individual towers, And so we have a small increase in the constant term as you go out in pseudo-rapidity. So it starts at 0.7%, it goes up to 1.1% at the most forward towers. And the overall sampling resolution is 12.6% over ET. So we put in all of that, all of those pieces to the model of the electron energy response and resolution. And again, we blinded the Z-mass. So the last step was to measure the Z-mass, and it had the same blinding offset as the muons. We unblinded them together, and we obtained similar values. So it's something again very consistent with LEP, with less precision because of the regions in the calibrator that we had to cut out where there were the light guides and so on. So there's less fiducial coverage, but we still get we get enough to make a measurement of the Z-mass. And as a consistency check, just because we're transferring the track momentum to the calorimeter energy, we check that the track mass that we measure just from the electron tracks is also consistent with the LEP value. And so there's a smaller subset of tracks that we can use that aren't radiating, but so there's a higher uncertainty, but again, it's consistent with the LEP value. So these are, the plot on the left shows you the distribution from the calorimeter energy for the best fit Z-mass, and the one on the right is from the track mass, which is a bit broader and not quite as many events. Okay, so that completes the charge lepton calibrations. So the last calibration is the recoil momentum, which is really the most complex of these. So again, we want to go through the similar steps. First is to make sure the data is as uniform as possible. By in here we worry about the shape of the recoil, the distribution phi. So here one thing that affects this distribution is misalignments of the calorimeter relative to the beam axis. So if there are two calorimeters east and west, so if they're depending on, we align each of them separately so that using minimum bias data so that we don't get oscillations in phi. So if you're closer to one axis, beam is, if you're off center and you're closer to one calorimeter, you'll get more recoil in that direction. You'll get on average more recoil in that direction. You'll get this shape. And so we check that it's flat after we apply the corrections in min bias data, and then also in the W data. And so that makes the data as uniform in response as possible. And then the next step is then to, so we have the uniformity of the data. So then we have to define how we reconstruct the recoil. So here we need to remove, so we measure the recoil using all of the calorimeter towers, all of the calorimeter energy that we measure. But we can't include the energy that's in the towers where the electron or the muon have crossed, because that's not recoil energy, that's then energy coming from the leptons. And so we have to remove these windows. And so we remove these windows, and so we have to then model how in our simulation how much energy has been lost by removing these windows. And so we do this by in our simulation, we create a distribution from the W events using towers rotated by 90 degrees. And so we have an energy distribution from these towers from W events. And then we have to parameterize the dependence of depending on whether the recoil has gone along the direction of the charged lepton or opposite or perpendicular, and how much recoil there is. So there's a few, and where in rapidity is, so there's a few corrections that we made, scalings that we make depending on the recoil in the event in our simulation. And so we can validate all, this procedure by looking at the data in towers rotated by 180 degrees from the charged lepton, so opposite direction of the charged lepton. We can look at the energy in the data, the energy in an equivalent tower in the data, and we can also look at what a simulation would give for that energy, and this is an example as a function of the recoil projected along that direction. So when the recoil is in the direction that your tower is, or effectively your charged lepton would be, you can have a GeV of underlying event under that tower. And you look in the opposite direction, you get as maybe half a GeV, and you have some difference here, which we take as systematic, and it's about an MeV effect on the W mass. So that's the definition of the recoil. So now we have to calibrate it. So we calibrate the response. So to do this, we use Z events, and so we balance the recoil of the Z against the direction of the momentum of the Z. So we can measure that with the two charged leptons, and this eta direction is the PT is along the direction of the PT of the Z. And so we have a response function between the two, and we apply the response function to the rapidity of the Z, and we add that to the recoil, and we get and so this should be roughly 0 for a response function is matching what the recoil response is, and it's roughly 0. And then there's some effect from the Muon resolutions that make it go a little bit away from 0 as you go to higher momentum. But you can then also plot the response, which is the ratio of the it's the measured recoil projected along the PT of the Z divided by the PT of the Z. And so this is about 50% response at 5 GeV of PT, and then about 70%. And you can see the simulation and the data match very well for that once it's calibrated. So that's calibrating the response. And so the last step in the recoil is calibrating the resolution. There's a lot of components in recoil resolution. There's a jet-like energy response. So you have some sampling fraction that grows root PT of the Z. And so that's what shows this rise along the PT of the Z, this resolution along the PT of the Z. At low PT of the Z, you're dominated by underlying event and pileup. And so that's, to model that, we take the sum ET of the event, which so just an overall resolution effect from all of the energy in the event. And so it's the square root of sum ET gives us the resolution for that, and the square root of sum ET is something we can check between our simulation and the data, and that's shown in the bottom plot here. The other thing we have to model is the angular resolution of the jet, so that increases the resolution. That gives some PT dependence to the direction perpendicular to the ZPT, because the angular resolution is not perfect. So as you get higher and higher ZPT, you get increasing resolution perpendicular to the Z because of this angular resolution. And so we need to model this. We have several bins in PT ranges of the Z, and as you go to higher PT, it gets narrower, and at low PT it's very broad. So we have a few such modeling parameters for that. And then we also have some parameters to model the higher order moments of the resolution distributions. So in the case of along the direction of the ZPT, there's you have the jet-like energy dependence, but then you also have a contribution that contributes that gives you a bit more at lower PT. We have dijet fractions, so we have a dijet fraction term as well, and so we get this improves the modeling of all of the moments of the distribution. So that gives the full model of the recoil. And so in order to check the recoil, we use W events, and the most important distribution in the W events for testing the recoil model is the recoil projected along the direction of the charged lepton. And this is because if you expand the transverse mass in the quantity of the PT of the lepton and the recoil along that direction, you parallel. To first order, the transverse mass is twice the PT of the lepton plus U parallel. So if you have a bias in U parallel, you expect an equivalent bias in the mass and that you measure. And so we check this distribution. We focus mainly on the means of this distribution, which agree to 1 sigma in the muons and also in the electrons on the left and the right. And so the simulation includes uncertainties from the variation of all of the recoil parameters that we fix using Z data. In the chi-square, we're just showing the statistical comparison between the simulation and the data, which doesn't include all of the recoil variations. So in this case, it's not great because it's not including all of the uncertainty from the Z fixing the parameters. Okay, so that completes all of the calibration steps and the validation of the calibrations. So the last few steps before you measure the mass are to define the sample and understand the backgrounds and the production and so on. So I'll show a little bit about that before getting to the final fits. So to select the events, we use triggers with lower momentum thresholds and very loose lepton ID. And in particular, both online and offline, our ID has no isolation requirement, and it leads to only a few percent inefficiency as you go to larger values of recoil, recoil projected along the charged lepton. So you would expect more inefficiency as the recoil is going in the direction of your lepton. Particularly if you have isolation, you're gonna have a big inefficiency because you have recoil all going in that direction and killing your ID. But without the isolation requirement, we have only a couple percent correction effect both in electrons and muons. And we measure this with Z data, and we apply this function to the simulation to model the effect of the identification. We're able to have such loose ID because we have a very tight recoil requirement, U less than 15 GeV. And with the kinematic requirements of charged lepton CPT of 30 GeV, that keeps the background, the jet background particularly quite low. And so we get, with the selection, we get a couple million of each of W to mu nu and W nu with some more muon candidates than electrons, because again of the cutting out regions of the calendar. So with this sample, so you have to understand the backgrounds after you define the selections. So the main backgrounds, the biggest backgrounds are the electroweak backgrounds. In particular, the Z to mu mu is about almost 7.5%. And this is because we have a muon chamber that's very central. So it goes out to rapidity of 1. We remove a bit more out to about 1.4 with our tracker. But then beyond that, if the muon goes in that direction, we don't reconstruct it. And so we just, Z to mu mu events should look just like W to mu nu events because we've lost a muon. And so we model this with our fast simulation, tuned fast simulation, also comparing to the full simulation and tuning various things like the MIP energies with the data. And this distribution is shown in dominantly this gray distribution in the W to mu nu sample is coming from Z to mu mu. The next largest background is W to tau nu. And there we again model it with our fast simulation. And there you just need to model the tau decay, and you get an order 1% background in each channel. And it's peaking at much lower momentum because you're losing much of the momentum to neutrinos. The other background that you worry about is the hadrons misreconstructed as leptons. We estimate this with several data methods in each channel, and we get 0.2% in the muons and 0.3% in the electrons, and so yeah, that leads to a small MeV or so uncertainty on the measurement from those backgrounds. Okay, so that's the background. So the last step really is to understand the production mechanism and put in some tunings for the production of the W boson. So the main thing here we worried about was the boson PT, because this impacts the PT distribution of the decay leptons. We used resbos to generate events with non-perturbative parameters and NNLL resummation, because we want to model the region of where the peak is on the PT spectrum. So this is Z to mu mu events. So we can tune we can reconstruct this fully and tune the parameter modeling where the peak distribution is the non-perturbative parameter. We can also tune the tail, the amount of events in the tail using alpha S. So it's an effective parameterization of alpha S of the tail. And so we with those two parameters, we modeled the W boson PT well. We looked at the impact of theory uncertainties, scale variations, resummation variations, scale variations on the ratio of this WPT to the ZPT, and we varied, using those shapes, we varied the W to Z ratio, and we constrained it with the data. We didn't, in principle, we were fit for the best fit value, but it was consistent with the nominal resbos, so we didn't make any adjustment to the spectrum. Yeah, so that gives us the WPT, determination and the calibration. The other thing we have to model are the proton distributions. So here we have so if we have some small rapidity range. So we need to model the proton distribution. So how much going more forward versus more central, because that changes the PT spectrum of the that we measure, the charged leptons and the neutrinos. And so we applied a correction. We obtained from the author's resbos. So we had a nominal sample, which is CTEX 6M, and we obtained from the authors also and then PDF 3.1 sample. So then we applied a small correction to update the PDFs to that sample, and then we used the principal component analysis to estimate the uncertainty on the PDFs. And we also then compared various PDFs to see that the range was within that uncertainty. We also have to worry about the final state radiation, and so there we use photos to model the final state radiation. There's a couple hundred MeV of energy lost as the charged lepton after the W boson decay, and so you have to correct for that. The photos summation, we estimate to have a few MeV residual uncertainty on that couple hundred MeV radiation. So all of those pieces now are in, and we can then measure these distributions, measure the W mass from these distributions, and so the measurement had a blinding offset of between plus or minus 50 MeV until we finished all the previous steps. So we could look at the distributions like this without looking at the value. And we could look at the residuals, and these are the MT distributions for the muons and the electrons. We also measure the mass using the charged lepton PT, and this is again for the muons and the electrons. And then finally, we also include the missing PT, the neutrino momentum, the neutrino PT momentum distribution that we measure. And so we can put all of these fits for the W mass together to obtain a final result, which if we put them all together, we get 8433.5 MeV plus or minus 9.4 MeV. And we can also split them up into different pieces, into just the NT fit, just the charged lepton PT fit, just the neutrino PT fit, or for example, just the electrons and just the muons. In all cases, they all are consistent with each other. We can further split up the sample into so it's an inclusive measurement. So there's a number of splittings that we can do, but then there are other splittings that would require full recalibration. So the charge splitting by charged lepton plus and minus we can do because we've done this whole alignment procedure and understood the effects of the bias in the charged leptons. And so we can estimate an uncertainty, which is this 12.7 COT is an alignment uncertainty from the difference in those charged lepton W mass measures from the two different charged leptons. And so that gives us a consistent result between those two for the muons. In the electrons, we don't expect any difference in reconstructing pluses and minuses. The only difference is charge asymmetry. So you get more in one direction versus the other direction. So if there's some miscalibration east versus west, that would show up, and so you see something less than 1 sigma, but you can even further calibrate that away using ERP to get to something that's consistent with 0. That's basically 0. You can also you can split up in phi in several ways. So we looked at sort of phi greater than 0, phi less than 0, and so again we could calibrate that way. In electrons, we don't expect an effect. In the muons, it's a little more than 1 sigma. And then the last one we do is splitting up the momentum scale calibration into 2 different run ranges. So in the first half of the data set and the second half of the data set, so the muon chamber, the electron, the muon momentum scale from the tracking chamber, we expect to be constant in time, that there's no time dependence we expect from this tracking chamber. We don't see any effect there. For the electrons, we have some calibration as a function of time that has some that is somewhat coarse due to just a mean over p calibration. So there's maybe some 2 sigma residual variation, which is less than. So this effectively goes into the constant term, and this is a 0.1% effect on a order 1% constant term. So that's still quite small compared to the constant term. So we put all that together. Yeah, so that's the final measurement. And so just to summarize, I hope I convinced you the W mass is an important parameter to measure in particle physics, and that and I've shown that this measurement with better than 10 MeV precision has been achieved with the complete CDF data set. It's the result of more than 20 years of experience with this detector. And in order to do this measurement at this level of precision, 0.01% precision, it required a lot of flexibility. We had to control all aspects of the measurement. So starting from the reconstruction and doing the alignment, and then reconstructing the data with new alignments, doing all of the calibrations, developing the custom simulation, doing all of the analysis. So all this we needed to do to be able to adjust to effects that we saw in the data. The analysis procedure was approved pre-unblinding, and the procedure was frozen, and we got this surprising 0.1% deviation from the standard model, which I think is interesting in many ways. It motivates us to think about how the measurements are being done, and how all the cross checks that are being done, and ways to further improve those and the procedures. But it also suggests maybe there's something beyond the standard model as well. So we'll see. Thank you.